Today we are going to learn about the topic of surfactants. Here I would like to introduce you to Irving Langmuir, a Nobel Prize winner in chemistry at 1932. He is a father of surface chemistry, which he detected the arrangement and presentation of surfactant on top of the surface. So what Irving Langmuir did was, he performed an experiment using carboxylic acid with various molecular weight. So what Langmuir did was, using this apparatus, which he called trough, okay, and he dropped a few of his solution of carboxylic acid on top of the surface of trough, and here is the water, okay. And when this organic solution have dropped on top of the water, it's milled on top of the water, okay. And this is a movable barrier, whereby when this bar is moved to the left, then the smear area will be reduced, okay. And there is a very tiny detector, okay, that what you call a dipper, that they can sense. It can actually sense the tension or the pressure exerted by this smear film of organic. So what Langmuir did was introducing various solution of carboxylic acid, okay, acid, and then measure its pressure using this dipper, okay. And the result he got will be presented in the next slide. So before we go into the result, this is the apparatus in real, that how the Langmuir experiments were performed, okay. And when they start to move the movable bar, this movable bar will be moving down, okay. And the area for smearing the organic solution is reduced, and there is this small little dipper at the end of this machine, that they can sense the pressure of the surface and record it in number, okay. And this is the pressure recorded, okay. And you can see when the area reducing, the pressure increase. So with the various solution of carboxylic acid, Langmuir found the result of this graph, where when he start to plot the film pressure against the area of molecule, okay. And it is noted that despite the different carbon atom in the molecule of the organic solvent, okay, the maximum pressure generated from the film will actually meet at this point, which is here, around 21, okay, around 21. So they will eventually meet at the pressure of 21 dyne per cm. So with that, Langmuir start to think, maybe even though when you have a different carbon number of carbon, okay, for example, you have number of carbon C, 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 and you have OH, and you have a longer C, okay, a longer one, and with an OH. And when they generate the same film pressure, Langmuir start to think maybe it's only the OH is attached to the water, and the rest of the chain, side chain, actually not in contact to the water. So this will be their representation. So this is the OH here, OH here, so OH here, OH here. So regardless how long their hydrocarbon, okay, they will actually, as long as the OH atom they have the similar size, they will actually contributed to the same film pressure. This is the conclusion of the Langmuir when he performed this experiment. So here is the detail of his result. When he noticed most of the carboxylic acid give rise to more and less the similar cross-section film pressure, okay. However, there is exceptional, for example, triolin and trielidine, okay. And with that, he tried to look into the structure of this compound, and this is what he got. And he found out that most of the hydrocarbon is in 3 dimensions. They are not a linear hydrocarbon, okay. They are in side change, okay, side change. That's why they doesn't really obey the rules that they will meet at the same point of 21 dyne per cm. So with the simple but informative experiment performed by Langmuir, it gave rise to what you call surfactants, which is surface active agent, okay. Surfactant is an amphiphile where the molecules arrange themselves in the molecular level, where all the molecules were stood on the surface of water. This is how they actually stand on the surface of water, and they have the hydrophobic group that attach covalently to the hydrophilic group, which is attached to the water. So surfactants is a surface active compound that they are active only at the surface, okay, and they have what you call a hydrophilic group, which is water liking, and the hydrophobic group, which is water hating. And the combination of both surfactant in one molecule called amphipathic molecule, okay. And it is the amphiphilic nature of surface active agent that causes them to be absorbed at the interface, whether they are liquid gas or liquid interface. And in an aqueous dispersion of amyl alcohol, the polar alcoholic group is able to associate with the water molecule, and the non-polar portion is actually rejected. However, because of the adhesive force it can develop with the water are small in comparison to the cohesive force between the adjacent water molecule. As a result, the amphiphile is absorbed at the interface like this, okay. At the air-water interface, the lipophilic chains are directed upward into the air and the oil-water interface at the oil-water interface, and they are associated with the oil phase. For amphiphile to be concentrated at interface, it must be balanced with the proper amount of water and oil-soluble groups, okay. Means it cannot be too long, cannot be too short. Okay, if the molecule is too hydrophilic, which is too short, it remains within the body of the aqueous phase and exerts no effect at the interface. Likewise, if it is too lipophilic, it dissolves completely in the oil and little appears at the interface. Okay, a molecule and ion are absorbed at interface are termed as surface active agent or surfactant. This is just a repeat, okay, or alternatively you can call them amphiphile. Okay, depending on the number or nature of the polar and the non-polar group present, the amplifier may be predominantly hydrophilic, lipophilic, or reasonably well balanced between these two extremes. For example, straight change alcohol, amine, and acid are amplifiers that change from being predominantly hydrophilic to lipophilic as the number of carbon atoms in the alkyl change is increased, and thus the ethyl alcohol is miscible with water in all proportion. In comparison, the aqueous solubility of amyl alcohol, which they have C5, is much reduced, whereas cetyl alcohol, where they have 16 carbon atoms, may be said to be strongly lipophilic and actually insoluble in water. So depending on the presence of ion in the surfactants molecule, they may be classified into two groups, which is ionic surfactants and non-ionic surfactants. And in ionic surfactants, it can be further divided into anionic surfactant, cationic surfactant, as well as zwitter ion. Okay, this is classification, example of classification of surfactants. When you have the ionic surfactant, for example, alkyl sulfate, okay, you have in the change an ionic charge, negative charge. And when you have the cationic surfactants, in their change, they are actually positive charge. The one with zwitter ion, in one molecule of surfactant, you have both positive and negative. And of course, when you have non-ionic, there's no charge on the molecule of surfactants. Okay, for ionic surfactants, let's talk about the anionic surfactants. The surface active part is anion, which is a negative ion. They are the methyl salt of long chain fatty acid, such as lauric acid, okay, or sodium dodecasulfate, sodium lauryl sulfate, which is generally used in toothpaste and ointment. Triethanolamine dodecasulfate is used in shampoo and also other cosmetics preparation. Okay, sodium dodecabenzene sulfonate is used in detergent and germicidal for germicidal properties. And the last example is a sodium dialkyl sulfosuccinate are good wetting agents. Okay, for cationic surfactants, these are chiefly quaternary ammonium compound. They have bacteriostatic activity, probably because they combine with the carboxylic group in the cell wall of microorganism by cation exchange, which cause the lysis of the cell. Okay, they may be used on the skin, especially in the cleaning of wound. And they are among the most popular antiseptic in this category are benzalkonium chloride, the preservative that you usually use in your pharmaceutical preparations, cetylpyrimidine chloride, and cetyl trimethyl ammonium bromides. Okay, an example of zwitter ionic surfactants, they are the least common one. For example, dodicel beta alanine. So for non-ionic surfactants, they are widely used in pharmaceutical formulation. For example, twin or span. Okay, they are polyethylene oxide products. Okay, surfactants that based on surfactant are of pharmaceutical importance, and esterification of the primary hydroxyl group with lauric, palmitic, stearic, and oleic acid form surfactant monolaurate, monopalmitate, monostearate, or monooleate. And these are water-insoluble surfactants called span. Okay, an addition of 20 ethylene oxide molecule produce the water-soluble surfactants, which you call polysorbate and twin. Okay. So example for surfactant ester, they supply commercially as span, and they are mixture of partial ester of sorbitol and mono and dianhydrides with oleic acid, and they are generally insoluble in water. Okay, they are used as a water in oil emulsifier as well as a wetting agent. Okay, for polysorbate, they are complex mixture of partial ester sorbitol and its mono and dianhydrates condensed with appropriate amount of ethylene oxide. So they are initially spent, and when you add in ethylene oxide, they become twin. Okay, and they are supplied commercially as twin, and they are mostly miscible with water as reflected in their high HLB value, and they are used as emulsifying agent for oil in water emulsion. Okay, proxamer is another example of non-ionic surfactants. They are synthetic block copolymer of hydrophilic polyoxylene and hydrophobic polyoxypropylene, and the general formula is EM, PN, EM, where E is oxyethylene, P is oxypropylene, okay, and the subscript N and N denote the change length, okay, the repeatability of the change. And properties such as viscosity, HRB, and physical state are very much dependent on the relative change length of the hydrophilic and hydrophobic blocks, and they are supplied commercially as pronic and are labeled using the pronic grid, for example F127 or L62. You don't need to remember the commercial name, but please do remember the chemical name. Okay, so proxamer, where the letter here indicates the physical state, okay, which denote solid, paste, or liquid. So this is solid, this is paste, and this is liquid. The last digit of this number is approximately 1/10 of the weight percentage of the polyoxylene, and the first one or 2 digit in the 3-digit number multiplied by 300 give you a rough estimation of molecular weight of this hydrophone. The relationship between hydrocarbon side change and surface activity is expressed as Traub rules. In dilute aqueous solution of surfactant belonging to any one homologous series, the molar concentration required to produce equal lowering of surface tension of water decrease threefold for each additional of CH2 in the hydrocarbon change of the solute. Okay, and this rule specifying that when you add CH2, one group of CH2, the surface tension of water will reduce 3 times. And this is the HRB system of hydrophile and lipophilic classification. Okay, and by means of this number system, it is possible to establish HRB range of optimum efficiency for each class of surfactants. More hydrophilic interface barrier favor water in oil emulsion, whereas the more non-polar barrier favor water in oil emulsion. For example, you choose emulsifying with a HRB3, okay, it will favor water in oil because this is more lipophilic. If you choose the one at high HRB, which is more hydrophilic, they will favor the formation of oil in water emulsion. The hydrophile and the lipophile balance number is a measure of balance between hydrophobic and hydrophilic portion of a surfactant. So the HRB of a surfactant is expressed using arbitrary scale, which for non-ionic surfactants range from 0 to 20. So it is only for non-ionic surfactants. In the stabilization of globule, it is essential that there is a degree of surfactant's hydrophilicity to confer an enthalpic stabilizing force and degree of hydrophobicity to secure the adsorption at oil-water interface. And the balance between the two will depend on the nature of the oil and the mixture of the surfactants, and hence the need to apply the HRB system. So in our next school year, we will learn about how to calculate the HRB system in order to stabilize the interface of two different phases. Okay, the higher the HRB of an agent, the more lipophilic it is. The span, for example, sorbitants, they are lipophilic surfactants with a low value, but with a twin, because of the polyoxyethylene ethylene side chain that is added to it, to the span, they are more hydrophilic and they have high value of HLB, so they will favor the formation of oil in water emulsion. Okay, so surface activity of drugs. There are some drugs actually they have surface activity because the molecule of this drug, they actually consist of the polar head as well as non-polar side chain. So it is a consequences of the amphipathic nature of the drugs. The hydrophobic portion of the drug molecule are in general more complex than those typical of surfactants, and often being composed of aromatic ring or heterocyclic ring system. So here are some of the example for drug that actually they show a surface active nature. For example, antidepressants, some of them are cropamazine, amitriptyline, okay, diphenhydramine, bromophenramine, orphanedrine, and the last one here. Okay, how to determine HLB? So the HLB number of a surfactants is calculated according to the empirical molecule formula. For non-ionic surfactants, the value range from 0 to 20 on the arbitrarily scale. To maintain stability, an excess of surfactants is required in a continuous phase. So hence, in general, water-soluble surfactants stabilize oil in water emulsion, and water-insoluble surfactants stabilize water in oil emulsion. And the HLB of non-ionic surfactants, where they have only hydrophilic, where the only hydrophilic portion is polyoxylene, is calculated by using this equation. So E is the percentage by weight of ethylene oxide. I guess you have learned this in your dosage form design in your first year. So here are some examples of calculation. So what is the HLB value of these products? Okay, where this product they have 20 mole of oxalate of oxyl alcohol. So the answer is, the E is the percentage of weight of oxylene oxide. So calculate the molecular weight of 20 mole of this. Okay, 1 mole is equals to 44, so 20 is equals to 880. Add this number to the molecular weight of oleoyl alcohol, okay, which having this molecular weight, and you have the total molecular weight. And what is the percentage of 1150? This is belongs to 880. So then you can calculate the percentage, which is 76.5%, and you got the E. So how to calculate the HLB? When you have the HLB and you have the E, which is 76.5, divide by 5, then you will have 15.3. So the HLB of this product is 15.3. So the HLB number of polyhydric alcohol fatty acid esters, such as glyceryl monostearate, can be estimated by using this following formula. HLB is equals to 20, 1 minus saponin number, divided by A is the acid number of the fatty acid. Okay, the HLB of polysorbate twin, calculating using this formula, is 16.7, with the S of 45.5 and A of 276. And typically the twin surfactants have a value in the range of 9.6 to 16.7. So even though twin, you can use this formula to calculate. Okay, and typically the span have the value of lower range, which is 1.8 to 8.6. The saponification number of ester represent the number of milligram of alkaline required to hydrolyze 1 gram of the ester. Okay, usually you need to perform the experiment, then you will know what is the saponification number. And when the ester is an oil or fat, the esterification lead to the formation of salt. which is why the esterification reaction is called saponification. As most of the mass of oil or fat is in fatty acid, it is a measure of average molecular weight of all the fatty acid present. And the acid number is the number of milligram of KOH required to neutralize 1 gram of fatty acid. Again, you need to perform experiment to know the number, the acid number. And the acid number is a measure of number of carboxylic acid group in the fatty acid. And the HLB number of surfactant with no saponification number, or it is not possible to obtain saponification number, can be actually estimated by using the following formula. HLB is equal to E plus P divided by 5, and E is the percentage by weight of ethylene oxide change, and P is the percentage by weight of polyhydrate alcohol, and then you divide by 5. You will get your HLB. Example, when you have a polysorbate 20, which is also twin 20, has a molecular weight of approximately 1300 and contain 20 oxyethylene group and 2 surfactant ring. So using this formula, okay, you can actually calculate their HLB. So E is the percentage by weight of oxyethylene side change. Okay, so oxyethylene is 44 times the 20 groups here, okay, then divide by the total molecular weight, and you got the percentage by weight, and P is the percentage by weight of polyhydrate alcohol groups, okay, in the molecule. So in this case, for twin 20, the polyhydrate alcohol group is 182, and the total is 1300, and then you have what you call the percentage by weight, and the HLB of both, HLB of the whole molecule, using this formula you can calculate this one plus this one, divide by 5, and is 16.4. Okay, and here are some of the example of HLB that has been determined. Okay, and the HLB system has been put on a more quantitative basis by Davis, who calculated the group contribution to the HLB number such that the HLB was obtained from the summation of hydrophilic group number minus the lipophilic group number plus 7. This is another formula. So the group number is assigned here. So whenever you have the group of, for example, 1 CH, then you plus 0.475, and then you have to calculate how many CH in your molecule, and then you sum them and minus the lipophilic part. Okay, then you plus 7, then you will get the HLB of the substance that you want. Okay, so here I end our lecture about surfactants, and thank you for listening.